Well, welcome everybody. I think, can you check if people are listening? No problem. Okay. All right. So, welcome to the October 10 presentation, STLE. Just for knowledge, for the people in the room, we are live streaming that. For the people connected, we have a fantastic crowd here. Got we got fed and we got some networking going on before starting the meeting. I'm gonna go through the briefly through the list of sponsors that help us doing these kind of events. You can see the list there on the screen. We have Petro Canada Lubricants, Canoil Canada, Unipex, Brentac, WearCheck, Lubrisol, Celis, LV Lomas, and Lanxess. So that's a commitment that we have to our sponsors to mention the names every first part of the meetings. Well, we are excited today of having a presentation by Blair Fraser. He is the Vice President of UE Systems, has over 25 years of experience in the manufacturing sector, deeply rooted in automation engineering. Beyond his contributions at UE Systems, Blair's entrepreneurial acumen is evident in his co-founding of the industrial AI company, Quartic AI. Moreover, he was pivotal in initiating and nurturing business units at Lakeside Process Controls and Emerson Impact Partner. Recognized as a leader in the industrial Internet of Things, Blair's innovations in connected ultrasonic tools have been instrumental for predictive maintenance and energy conservation. His strategic insights have fostered industry collaborations, technical publications, and patents, further underline his role as a thought leader in the field. Can be also tough. So before passing the mic to Blair, I'm just gonna mention a little bit briefly. His what we already circulated. The topic of conversation today is unleashing the power of wireless autonomous bearing monitoring and lubrication. In his thought-provoking talk, we dive into the new era of wireless autonomous bearing monitoring and lubrication, discover how UE system cutting-edge technologies are revolutionizing maintenance practices, leading to enhanced equipment performance and operational efficiency. Join us as we explore the latest advancements in wireless ultrasound, vibration, and temperature sensor, specifically focusing on bearing monitoring and lubrication. Well, I'm gonna just code it there and then pass the mic to our speaker today. Thank you for. Thank you. Yeah.
I would have made that bio shorter if I knew you were going to read it.
Yeah,
I promise that, but
mention a little bit about yourself.
you can pull the presentation, or
Yes.
that's perfect. Thank you. Okay, perfect. Thank you. Well, thank you, and thank you for hosting me. It's a pleasure to be here today. I know some of you can't see me, so I'll do my best to describing anything I'm going to do physically in front of you for those that are on the call. So we are going to talk about bearing health monitoring. I'm going to go through a quick overview of what ultrasound is and how it applies to lubrication. So first of all, I always like to start off with a scenario, and it's something, and I guess my bio was indicative of that I've been in this space of a race to track a problem with an asset or a piece of equipment, and in particular, rotating equipment, right? So all across all industries, everybody has these pieces of equipment, and that's why we're here, that move in a circle, right? And we need to keep them properly lubricated. And what's happened in the space I'm in around the industrial Internet of Things is it's something I call a race to detect a problem. Okay, so what technology can first detect that there's something going wrong with their piece of equipment, which is great. And that's this first scenario here, which is this defect detected. So essentially, when you look at an alert like this, now I made this alert up, this is in my language, but essentially, as we talk about bearings in particular, there's something wrong with them. Something's already happened by the time technology picks it up, right? And if anyone understands, if he goes back to late 1960s, there's two gentlemen named Nolan and Heaps that started RCM, Reliable Centered Maintenance, and they did a study on the airline industry. And they identified this, what's called the P to F curve. And P is when there's an identifiable physical condition. And the F is when there's a functional failure. So that identifiable condition is something that has already gone wrong in a bearing. The other scenario that we're really working towards, and we believe that that old adage of, an ounce of cure is worth a pound of prevention, right? That there is value in stopping that defect from happening in the first place. So there's really two types of alerts we're trying to focus here. One is there's a defect detected, but I think if we take a little bit of the investment that we're spending on detecting a failure and put that to where you guys are around the lubrication, and I'll get to why lubrication is so important. I know I'm preaching to the choir, but if you have the ability to prevent that failure from happening in the first place, don't you think that would be a better place to put technology? And that's what we're going after. And it's a very unique insight we're trying to offer here. In fact, when I ask people, would you rather have option 1 or option 2 for an alert? The right answer is I want both. So when we go back to that Nolan Heaps, and I guess for those in the room, I can't see those online. Has anyone had any education around reliability centered maintenance before? Right. So this might be not anyone that's in our field, and I say ours and UE systems understands, and we are always been told you cannot have a presentation unless you have a P to F curve into it. Right. And where ultrasound fits, and undeniably, and if you go back, it was actually a study done by NASA looking at bearing defects and the technology that could first, what they called the detect the first incipient fault within a bearing. And ultrasound, or acoustics emission as it's otherwise known as, was the first technology to pick up a defect, right? And over the years and decades, where it really came into fruition was not only detecting that issue, but moving back before there was an issue to where we could see a problem with lubrication. So we could literally hear and measure the ultrasound emissions that are leading to that bearing needing lubrication, or of course it failing. Now this is before, and now I'm talking specifically from a bearing aspect point of view, before vibration, before there's a change in temperature, and of course before you can hear, smell, and sometimes even taste it. So when we're looking at ultrasound, we're looking at detecting that failure, but we're looking at those very, very subtle signs that there's something in that bearing, that bearing needs a little bit of care from us. I keep on wanting to hit the other button here. And this was SKF study, and I heard you guys talking about going through SKF, and it was a great study, and Timken, all the bearing manufacturers and third party has similar studies. Now it does vary between 60 to 80%. And what I'm talking about here is rolling out bearings, right? So we're talking about grease lubricated bearings. So up to 80% of premature bearing failures can be traced back to a problem with lubrication. Now, the reality is, in the industry I come in, it's all throughout all manufacturing, all industries. It doesn't matter if that's 60%, 80% still. The reason why I believe this society exists is we know that lubrication has an important piece to keeping our assets going. But if you look at that study and you dive a little bit deeper, when you look at how they quantified that 80%, and I don't know if I can move that this around so those in the audience can see it, but it's not just the right amount of grease. Let me move it. There we go. So it's about not renewing it, right, in a significant amount of time. So you still have the grease properties in there, but chances are the oil's gone, the thickener's gone, things like that, right? And one of the big things we see in our industry is just the wrong grease is being used. It's still very, very common to see electric motor have the same grease as whatever asset is driving, a pump, a fan. And most of us, I think, know that that's probably not the right choice in that application. So when we start to look at what has the industry done, now this is the timeline according to Blair. Okay, so it's not technically, there are some challenges to this, but there's still people out there, and I'm sure you come across them in your meetings, that are doing what I would call whatever lubrication. I grease this bearing whenever I want to, whenever I can, whenever I get to it, right? you fast forward a few decades, and we got really good at using a calendar and a calculator. I'm sure some of you have seen the calculator to calculate the quantity and regreasing frequency, right? There's a number of calculators out there, and if you look at them, they sometimes get you into the ballpark. They sometimes get you into the right application. But if you look at those calculations, there's a number of variables you have to, I was going to say guess. Sometimes it's more of an educated guess. But as we are here in Canada, if you use that calculator and if you have an asset out on the roof or outside, right, temperature, just the ambient temperature is one of those variables. So if you change that temperature, so we go back last week, what was the temperature here? 30 degrees. This week, unfortunately, it's not 30 degrees, right? So if you were to change that differential of 20 degrees in that calculator, it's going to give you two very, very different numbers, right? But how often do you see people using that calculator based on operating conditions? Very little. So it did okay. And then what we call condition-based or friction-based, ultrasound-based condition lubrication came out, which we were listening and monitoring that friction in the bearing to decide when and how much lubrication we should apply to that bearing. At around the same time, and this was accelerated during COVID, during the pandemic. And for those, well, maybe you can see me, I'm holding up a single point lubricator. How many people have seen these before, right? These little dangerous things that sit out there autonomously greasing based on time. So because during the pandemic, a lot of us weren't able to access the plants, the sales of these little devices went up astronomically, right? And when we started asking our customers, do you use them? It was a love-hate relationship with them because they're sitting out there on equipment. And what you end up having to do is to go out there and periodically check the lubricator that's meant to remove a task of going out to lubricate. Why? Because the battery can die, they can fall off. We've seen where maintenance has unintentionally taken them off, got to put them back on. So what came about in the last 2.5 years, and there's a reason why it took us a little bit longer to come up with this solution, and for those, I'm holding this up for you guys and I'm holding it up for you guys, is could we combine our technology around our handhelds where you went out to a piece of equipment, you listened and trended a bearing and monitored its friction, and then if it needed grease, you went in there and you lubricated it? And could we combine that with a single point lubricator so it only dispenses grease when it's needed? Right? And that's essentially what this technology is doing now. Now, of course, we're doing this all wirelessly. And I'll walk you through some case studies of how this works. So as I talk about this, there's going to be really 4 main parts about this. We have our sensor here. This is monitoring the friction in the bearing. It's also measuring the vibration and the temperature for an overall asset health of that bearing. And then we have our single point lubricator, which is called the BTUE, which is a Bluetooth lubricator, which you could, if you had the app, you could make this go off if you knew the password and how it was encrypted. And we have our software platform that ties everything together. So essentially what we're doing is we're trying to eliminate the guesswork from lubrication. So we're combining the ultrasound, the vibration, the temperature to form a solution that was formerly siloed. It was, you had the single point lubricator and typically you had your vibration monitoring system. We've combine them both into one solution here with the goal of removing the guesswork, but also monitoring the health of our bearings past a lubrication failure mode. So when we look at that sensor, it's an ultrasound first sensor. So I'm going to play some, hopefully I can play audio on this. We'll try. For those that are here, we'll find out if it works, but if it doesn't, I'll do my best to reenact the noise. Then we have the vibration sensor. We have audio on demand, which means this sensor could be in Australia right now. And through the platform, you could actually physically listen to that bearing. And why do we do that? Because there's still human expertise that's required, I believe, in all systems. And if you heard my bio, I do have extensive background in artificial intelligence, and I do feel there's a place for it. But I think it's going to be very much complementing experts and humans in the loop versus replacing them. So we wanted the ability for humans to be able to listen to that bearing no matter they were. And temperature. And we all know from that point, if your temperature is going up in that bearing, you know, there's other things that should have been caught before then, right? But it is our last ditch effort to catch a failure. And then when we look at with this sensor, with the capabilities of ultrasound, vibration, and temperature, what type of failure modes can we focus on? Well, if you look at the bearing faults, the machine faults, Those are, once an issue is already detected. What we're trying to focus on and put a lot of weight on is those faults to the left of lack of lubrication, over lubrication. And I do have a Strybeck curve here I got to pull up. We'll go over those. And then, of course, precision lubrication. So this is what that data looks like. And it looks like a lot of squiggly lines. Now, if you're an engineer, you're going to understand or love these squiggly lines. But what we tried to do is, and we can show you what this, if we have time, what this looks like live. But we're trying to build insights out of data, right? So everyone says in the world of Industry 4.0 or AI that data is the new gold. I don't believe it is. Data is the fuel for it. It's the iron ore, if you will, if you're in mining, right? But really, the insights is what we're looking for is the goal. So try to make it, is this misalignment? Does it need lubrication? If it does need lubrication, how much grease does it need? Those are the fundamental questions we're trying to ask. Okay. Now I know I'm preaching to the choir here on the Strybeck curve. I'm assuming most people have seen the Strybeck curve. Okay. So essentially what we're doing with this sensor is we're measuring, we're gamifying where we are on this Strybeck curve. So, and I'm going to show you how we're doing that. I'm trying to take the sensor off. So when this sensor is mounted on a bearing, we're measuring ultrasound, which is directly proportional to the friction level in that bearing. The more friction, the more acoustic energy it produces. And it's measured in a decibel scale. That decibel scale is logarithmic, and I'm going to show and prove this theory out to you guys. So you guys, I know I'm preaching the choir here about the boundary. So the boundary, the way I like to describe it, it's metal to metal, right? There's no lubricant in there. It's the highest friction we could ever get in that bearing, right? Even when a bearing completely fails and the rolling elements are on the floor, the friction actually goes down because there's nothing rubbing. It's just floating in air, right? Now the other side of that bearing's taking a heck of a load. So there's the boundary. We have the mixed and we have the hydrodynamic. Here's the interesting part. So as we go through this, and I'm assuming you can see my mouse. Yeah, so as we're going through this, right, we're adding grease, we're dropping that friction. We get to this point. If we keep on adding grease, what happens? That friction goes back up, right? So if you look at this, and this is the best I could draw the Strybeck curve in PowerPoint, so it's not the correct slope, but you get the picture, is that film thickness or how much grease we have in that bearing. So if you draw a straight line across that, and say we just walked up to a bearing and we put this sensor on, how do I know if I'm at this point of the Strybeck curve or I'm at this point? And I got all day. I'll sit here and wait because I still got about 30 minutes left on my clock. How do you think we would know where we were? I know it's late in the day. We all ate. So I'll give. What was the answer? No, so noise, yeah, but it's at the exact. So the noise level, which is indicative of the friction, is at the exact same level. We just don't know if we need to add more grease or we've already added too much. So I'm going to walk you through a scenario, and for those on the call. So right here, say I'm right here, and hopefully those on the call can see my cursor. If I'm right here, and I go up with the grease gun and add just a little more grease, what's going to happen? The friction is going to go down. Okay, so keep that in mind. Scenario one, if I am here and I add more grease, what's going to happen? The friction goes up. So the way we do this, like people think it's magical and it's scientific, but that's what we do when we have this system out there and we don't know where we're at, because the equipment we get put on is often not new. It's been used and abused for sometimes decades and decades, right? Sometimes we go up there and we see grease just coming out the bearing. It's on the floor. Sometimes you see the Zerk fitting and it hasn't been touched in a long time, right? So what we do is we put the sensor on and we put a little tiny amount of grease in. And we're starting to look for that change in friction. Sometimes we don't see it because sometimes the seals are blown and it goes right through there, right into the motor, right? So sometimes there are no change. But what we're looking for is that change in friction. So if we see that friction go up, we know we're already lubricated. We see that friction go down, it needs lubrication. There are scenarios in between. Does that make sense? Okay, this doesn't require sound. So what we're doing, and the picture that's in the image I want you to just picture, even if this was an audio sound, right? You were playing it on Spotify, what that would sound like, the magnitude. And the minute grease hits, that's that sound going down. That's that friction level going down. And the next slide, I'm going to play some sound clips, and hopefully it plays. If not, I'm happy to send it out after the fact or direct it to our website where we have tons of samples. What we're going to look at is this is an ultra probe. So what they're doing, and if you see the sensor, this sensor is listening to that bearing. And what you're going to see on the screen is a decibel level that is directly proportional to the friction. And as the person in the background is adding grease, I want you to watch that friction level on that screen start to drop. And I want you to go back to when I had that Strybeck curve up, because this person does a few things wrong when it comes to lubrication best practices, right? But the intent is to show you how it works. But also, if you want to comment on the lubrication practices, that would be good too. Okay, so we started off around 58 decibels. He's pumping a lot of grease into that bearing. Now, if there was audio, you would actually hear it, but that's fine. What's starting to happen here? It's going down. Whoa, did that drop? An 8 decibel change is doubling or either doubling in either direction the friction level. An 8 decibel change. So no, we're gonna get there, yeah. So remember what he got it, what was the lowest number he got it down to? 42, 40, somewhere in there, right? So what happened? Yeah, he went down that Strybeck, should have stopped, right? And this is where people say, like, you are turning this into a video game. And that wasn't our intent, but that's kind of what's happening. So this was the manual way of doing it, not the system we're going to talk about today. So if you watched him, we started off at 52, got it down pretty low, kept on pumping, and brought that back up. So now we're to the right of that Strybeck curve. We're actually adding that hydrodynamic where there's too much grease in that bearing. Those rolling elements are trying to fight its way through the seal, or in this case, likely a shield. So it does find a way out, right? But they stopped at 48. So 52 to 48 is still a pretty significant drop, and undoubtedly they saved some of that life of that bearing. Had they stopped earlier, that would have been the best scenario. What do you think about him and the rate of which grease was applied to that bearing? Not good, I can tell you that. So where we see in our industry from the lubrication side is, people don't kill. Grease guns don't kill bearings, people do. So the grease gun is a very important tool. And we need it to get grease into the bearing. They are capable sometimes up to 10, 15,000 PSI, right? So yeah, it was the rate of which he applied the grease to, right? And that comes down to human. Like, we don't like to wait. Watch pot never boils, right? Watching paint dry. We've all been there. So your first reaction is, well, let's just keep on grease until it sees, right? So when we automated this system, this puts out 0.33 grams or cc's of grease every 5 minutes. So it's the size of your thumbnail, right? So when this is automatically lubricating the bearings of your critical assets, your motors and your pumps, it can take 45 minutes, an hour for it to lubricate a bearing. So it's watching. The sensor is essentially measuring that friction just like it was on that video. And it's telling that luber, okay, just a little bit more. And it waits just a little bit more. And it can take 45 minutes. And it'll tell you every step of the way of what it's doing, how much grease, but it's going to put it in very, very slowly. Have you ever seen those grease guns that have, you can put a DeWalt drill on it essentially, and you can shoot it from, I'm from Waterloo. You can shoot grease from here to Waterloo, right? Those are getting dangerous. Those are just getting lazy. We have them to fill grease lines, but that's it. So that's how it works. So let's take a little deeper dive into this. So let me see if this will actually work. No, I guess there's nowhere to play sound. I will send these out after, and I do, let me just make sure. Yeah, there's no way of playing. Maybe you heard it on the call, but essentially, this is a sound you would hear when you lubricate that bearing. As you're lubricating that bearing, it's going to be very loud. There's going to be a lot of impacting, a lot of noise. Some people define it as gravel. you have a gravel in a can and you're shaking it around. That's what an unlubricated or an unlubricated bearing, and you'd hear that as you're applying grease, you'd hear it go shh. We call it the aha moment because you don't need to be a tribologist, you don't need to be an expert just to understand that dampening of that sound is what you're looking for. And this was an example, and again, I'll try to send this out after, is that bearing being lubricated, and this is exactly what happened in that previous video. They dropped it down, and guess what? They kept on lubricating, right? So you see it drop, and you see that sound come back up again. This is what the platform looks like. So when you're looking at it live, this is what the gamification looks like. So we have that friction level go up. And the way we determine when a bearing needs lubrication, a lot of people think we're throwing a dart at the wall, like, yeah, try here and see if it works. There is an ISO standard. There's an ISO standard that I can never remember the whole name of the ISO standard, but there's a bunch of numbers after ISO. And it's not the greatest read, but it does outline the limits for any bearing subject to change, subject to slow speed or very high speed. So slow speed less than 100 RPM, high speed once you get over around 1,000 RPM, or sorry, 10,000 RPM. Those limits do fall off, but there's an ISO limit that says 8 decibels of friction change over, I'm not sure where that changed, over your baseline, so over what the friction level normally is the first indication it needs lubrication. Okay, so an 8 decibel change. A 16 decibel change indicates you're beyond lubrication failure mode, and a 35 decibel change is that piece of equipment is walking down the hallway. It's gone. Now, I've seen it a few times, but we don't like to see it much. So you can see here, and I'm going to explain, the blue line is the friction, the orange is the impacting. I'm going to tell you why that's important, but if you look at this blue line, grease is added, and it starts to go down, right? Again, we call it that aha moment, because when you're remotely monitoring your bearings and you say, okay, go ahead and lubricate, or it does it for you, and you're watching that friction and you're watching that drop, it's a pretty amazing thing. So we start off with those ISO standards, and we will fine tune it based on the application. So what we want to do here is get as close as possible. We stop within 2 decibels of the baseline, saying that's enough. Don't get greedy, because the chances of over lubricating are pretty high. That's where we try to stop lubricating. So the system will automatically lubricate till it gets to 2 decibels within that baseline. Every bearing is going to have a different baseline. So when we look at how the sensor works, and again, I'll hold it up to the screen here, is technology in the IoT space has really changed the game. How far we see it in the consumer business with our headphones and things like that, right? They're constantly improving how crystal clear sound can be when you put in your Bose or your I'm not an Apple guy, whatever those things are called, those white things you put in your ears, I things, right? But the range of which they have been able to communicate now, and with the right gateway, we can get up to 1,300 feet from the sensor to a gateway, and we can talk to up to 40 of these devices. So you start to think about your assets throughout a plant. One gateway can cover a lot of assets, and all that information is meant to, whether you're a regulated utility or whether you're making cookies, right? There has to be different ways of getting that information out secure into platforms, and that's what we've built here. So again, I've talked about this at the start, is what we're trying to do is really give you a holistic view of the health and lubrication needs of your asset, and really transform that data into insights, and also guide people. So when you do have an issue that you can't solve with lubrication, what is likely the issue? Is it a bearing defect? Is there a loose belt? Is there misalignment? Is there a coupling issue? Things like that. So we've had a wired version of this product out for 2 years, well, 2.5 technically. And what was interesting is, best way to explain this. So we've known, because of our handheld instruments, using ultrasound-based lubrication, the grease savings that are possible. When we developed this system, what we found, and to my surprise, was we were lubricating bearings more frequently than we were catching with traditionally 1 month route-based inspection. So we would see a typical pillow block bearing ask for grease maybe once a week. And the whole premise and the whole company was built on, with ultrasound guided lubrication, you're not going to use as much grease. I thought to myself, could we be doing this wrong? And what we came to learn was, in order to maintain the ideal friction in the bearing based on that Strybeck curve, it requires grease more frequently, but significantly less. So the math worked out. Instead of saying going around, I'm going to put 10 grams of grease into this bearing every month, when you went around monthly and did it, it would only take 0.3 cc's every week to keep it happy. So while it was putting more grease in, it was putting grease in more frequently, the quantity was significantly less. Right? If you start to think about it, because you're constantly monitoring that Strybeck curve, oh, I need a little bit of grease. So you're constantly drip feeding it based on condition. And our whole goal of this system was to put it out there and save bearings. But that still wasn't the biggest benefit that our customers came back to us and told us. What did they tell us? Just the time savings of people, of going around there. And you guys would know this. How many lubricated assets are there in a facility? More than one, less than a gazillion, right? There's a lot. So that time saving seemed to be the biggest driver. And one of the things that we came up with is we learned through over 2 billion data points that we analyzed that there's really two variables that are most indicative of the lubrication needs of that bearing. The first one I'm going to talk about is at the bottom, which is friction. That friction is undoubtedly, that's the one that's been used for decades and decades. That tells you the lubrication needs. So it tells you when lubrication is required, and your goal is to drop that friction down to baseline. It tells you how much lubrication is required. And what we found, the value of impacting, of measuring just the impacting. So how many spikes do you have when you're looking at that time series data, is a very good indication of early signs that bearing needs lubrication, but more importantly, the severity of which it's failing. And I'm going to go through some case studies here at the end, and I'll say this repeatedly, is lubrication can mask a failure, but once a failure is already there, you cannot stop it from happening. And I'll set out to prove that. So this is a great example. So this is a lubrication example of a healthy bearing. If you look at before lubrication was added, look at the width of that. And if you imagine it playing, how loud that would be, but also take a look at the spikes. That's what's killing your bearings. It's those impactings. That's what's calling the pivoting, everything that's in your bearings. You lubricate, that friction drops, and look at the impacting. It dropped well within ideal ranges. So that's a great bearing. Let's take a look at a bearing that's lubricated that has severe issues. So we saw that same level of friction, the same level of impacting, but even after lubricating, that friction did go down. But look at the number of spikes or impacting that's in that bearing. So would you rather have this bearing or this bearing? Right? Yeah, that's right. You'd want this one. You want to control the friction and the impacting and guarantee that's going to save a lot of life into that bearing. And then the ability, again, we can't have sound here, but I will send those recordings. The ability to take the sound file, analyze it, so you can look at is it an inner race defect, an outer race defect, is possible. And then as we tied the system together, and for those of you, especially if you're on the call and you've used these single point lubricators, you're going to know exactly what I'm going to talk about with confidence about these single point lubricators that have been put out there in the hundreds of thousands, if not millions, across factory floors and plants, and really just in Ontario. Is these sit out autonomously. They are installed on bearings, and as I said, they sit out there all day, all night. Sometimes they're indoors, sometimes they're outdoors. And we asked our customers, do you use them? And if you do you like them? And they said, we use them, we don't like them. They either said, we use them because we have to, or I've used them, they're in the garbage, you can go get them, right? And the reason being is they build a lot of trust, but if they go wrong, they go wrong. You might not get back to it in a month, another 2 months, and it's not lubricating your bearings and your equipment fails. So what we wanted to do was build a smart. So through anywhere, through your cell phone, if the grease level gets low, it's going to send you alert. So anybody, our customers that have this, I say, if you run out of grease, you have chosen to ignore a bunch of alarms. Back pressure. So if you think about this, this can get mounted about 20 feet away from the bearing. So you can bring it outside of an unsafe area with guarding, things like that, and mount it 20 feet away, and it will push grease 850 PSI into that bearing. But what can happen with 20 feet of line? It can get cut, it can get plugged. So we built a back pressure in there. It's self-serving, one, and to your point about blowing out the seals, it will prevent you from blowing the seals out, right? It's not a human going like this that we saw. But number two, it's also going to try to save itself because I don't want to keep on replacing these. So it will stop and say, hey, too much back pressure detected. And of course, it is battery powered. If it's sitting out there, we're going to monitor the level in that bearing. And then one thing, as you guys are looking, or anybody that's out there is looking at new age IoT or Industry 4.0, whatever you want to call it, platforms, is especially as you get to regulated bodies with NERC, OPG, nuclear plants, you can't just have data going every which way, right? And that's what's happened. Everyone's built solutions on silos. Okay, if you want to use ours, you have to use our data. Let's go to our cloud. We're trying to build enterprise. We're building enterprise level systems. So if you want it in our cloud, great. You want it in your cloud, right? A big conglomerate company, has their own cloud, great. You want to keep it on premises where it never leaves that plant, proverbially the four walls, great. You have options. The system's designed to work on all three of those platforms, which to my understanding is an industry first. Okay, so we're going to start looking at some data here quickly. On this pillow block bearing, you see it's belt driven. This is our wired version I'm going to show you here. You can see the sensor that's monitoring that friction. Just like I showed you where that guy was using a handheld unit, it's doing the same thing, except you can't see a number, only if you have the platform up. It has an accelerometer, that's not ours. There is a vibration sensor that's on the strut that shouldn't be there, that likely fell off somewhere. And that copper tube line is the grease line coming in. Okay, so for context, it is on a variable frequency drive, and I can get into more details. So that blue squiggly line you see at the bottom is that friction in that bearing for a 24-hour period. Okay. Underneath there, if you look really faint, there is a green dash line. That's the baseline. That blue line, if you remember my comment, that is 8 decibels over the baseline, which means it needs lubrication. The yellow is the warning, and the red is uh-oh. Right? So this is what we want to see. A lot of people might look at this for the first time and see, hey, that blue line where you're monitoring that friction, it seems to have some peaks and valleys, and it does. No matter how good you installed that bearing, no matter how good you selected the grease, there's always, it's so sensitive. Our sensor, if you were to take it to your eyelids, take this sensor and put it to your eyelids, it could measure the friction of your eyelids hitting each other. Okay, so let that sink in, how sensitive that is. Now, you don't want to put this in a factory and someone goes by and blinks their eyes and you think a bearing's failing. So we automatically adjust that sensitivity based on the bearing noise. So this is very common. This is ideal. If I saw every customer's bearing data look like this, I'd be a happy man, but the reality is we don't. So to see these peaks and valleys is very, very typical. And it also tells us the sensor's alive. It's attached, it's working. You want to see these peaks and valleys. So here we are on this is driving a big fan. The sensor's in the background, the wired version, the single point lubricator's up front. It's the drive end of a motor. And I'll walk us through this. So what's happening here, if you see that green line, that's the baseline. Over time, this has gone up above that needs lubrication. You have 3 options at this point to configure the system. 1, it will send you alert. Really 2 options, I guess. 1, it'll send you alert, and you have to, once you have that, then you have 2 options. You can go through and say, I want to smart lube or manual lubricate it, which means you push the button, a known quantity of grease is going to come in. If you use the assist mode, it's going to do all the logic for you. So it's going to constantly monitor that strieback curve. If it ever sees that friction start to go up, guess what? It's going to stop automatically. If you ever reach the maximum capacity of that bearing, it's automatically going to stop, right? So there's safeguards in place. And the second option, if you get the alert, you can put it in fully automatic. And we always recommend not doing that for the first little bit until the system gets to learn your bearings, and then it will lubricate on your behalf. Some people always want humans in the loop, at least a human saying, okay, go lubricate and I'll watch you. So if you look at this, the friction went up, it went above that needs lubrication. It's bouncing around. You can see that impacting start to happen. And this is where the magic happens right here. The system kicks in, it lubricates that bearing. It drops that friction like a stone. Happens time and time again. That friction drops very aggressively. And if you look over here, what you can see here is lubricant volume used, 9 cc's or 9 grams. They used to put 50 plus into that bearing every time, every month, right? So significantly less. It was 4 days ago. So we keep track of all the grease that was used. So the end of the year, end of the month, you want to track your grease consumption, you easily can. So what we do is we store the baseline friction. It was 11. The friction, by the time it greased, went up to 22. If you remember my comment, 8 decibels, that's actually around 6, is around doubling the friction. So that friction level is quite high, and it brought it down to 12.6 all automatically, right? So that's pretty impressive from a bearing lubrication point of view. And if you look at, here's our lubricator. We have about 190 cc's or 190 grams left in that lubricator. So here's another great example. The friction went up, it lubricates, and it drops it down. Again, 7 cc's. We constantly see a small amount of volume of grease that's required to drop that friction level down. Now, this was a study. It was done by a laboratory in the States in Pennsylvania. And when I was talking to him, it happened to be at a conference. It was a lubrication conference. And he came up to me and introduced himself and said, I love what you guys are doing. If you guys know EPRI, which I'm sure you do, he did a study for EPRI around using acoustic monitoring and lubrications. I'm happy to share the paper with you. So they proved that with the right technology, you could do this. And I was just going through those billions of data points of data I was talking about. And an image like this came up, and he said, do you know what's happening when you see these spikes here? And I looked him dead in the eye, said, absolutely, and I had no clue. Right? I said, well, why don't you tell me what it is? And he brought me to his lab, and he had an open bearing, and he put plexiglass over so the grease would stay in, and he used different dyes in the bearing. And he was able to starve a bearing. And what we saw was these little explosions, and you probably saw it in your grease lab, these little explosion pulling from pockets of grease throughout the whole bearing when it was starving for grease. These little micro explosions. It looked like Disney fireworks, if you would. And that's exactly what's happening. So we can pick up these little subtle impulses, these impacting that's happening. And what we did is we walked up with the grease gun, not a DeWalt battery power, but the grease gun, just shoved a little bit of grease into there, and it just smoothed right out. Right? So that gives you the power of how sensitive these sensors are. Now, so those were all, except for the last one, were marketing pictures. Those are what you'll see on our website of everything being rosy and working just perfect. But what happens if you lubricate a bearing? That's bad. And I travel throughout North America, the world, and tell this story, and people in a northern climate get it right away. So the analogy I give is pick the 401, pick the Don Valley parking lot, whatever it is, and think about it from a perspective of a pothole. So if you have a pothole, the city will come in eventually, fill the pothole, right? So then your friction level's better with a car drawing over it, but each car that goes over it, what happens? You dig a little bit of that pothole up. And that's what we've seen time and time again from a lubrication point of view on a bad bearing. So you can see here the friction level went up. It's supposed to be at this green line. It went above the blue, hit the yellow. System lubricated, dropped it down. Looks like it was good, right? We filled the pothole. What happened to those rolling elements? Kept on going over and over and over it. So if you remember earlier, about 2.5 hours ago when I started this presentation, I started off saying lubrication can mask a failure. It can't cure it. Right? It's too late now. So what's happening here is that friction went down, but as those rolling elements started to go over it and over it and over it and over it, what happens? The friction level went back up. Right? The rate at which it went back up tells us a lot about the severity of the issue in the bearing as well. So to prove this out, what happened is, if you look at this, this was this year. So this was around April 6th, we lubricated it. This next one was April 20th, so 14 days later. Lubricated it again. Look how quick that friction came back. Right? Good indication that bearing is not healthy. Right? So that's why we have the manual button on the platform, on the on-track. Why? Because we have seen customers, I'm going to say, sacrifice grease to get through the next shutdown. And I nurse this bearing till I get to Sunday when we're going to shut down. At the cost of grease, at the cost of the environment, right? Is they're going to keep on putting grease into that bearing, into that bearing, into that bearing to save it. All right, I will open it up for questions. I think there's a chat somewhere, but if anyone's on the call, you're more than welcome to talk into my ear. I think I'll be able to hear it. Any questions in the audience here? Yeah, I'll repeat it so they can hear it as well. Oh, so how often is it calibrated? From an ultrasound point of view, it's not. From a vibration point of view, it's not. It has a reference standard that's in there that it references itself when it wakes up. So we take a reading every hour, and there's a reference chip in there that it uses for a reference point of view. From an ultrasound perspective, it doesn't measure in absolutes; it measures in differential. Right. So we're just concerned about the rate of change versus the absolute value. From a temperature and stuff, we only do it from factory, and we don't touch it ever again.
Depend on water, like food plant application.
Oh, yeah.
The ground mine they really like to power wash
They
everything.
they do. So you obviously came. So the question for those on the call is, have you ever done anything where there's been water ingress? And yes, we have, and we've seen that exact. So if everyone doesn't know the food and beverage industry, they'll pressure wash anything for 20 minutes. So we have seen it. In fact, I have a great case study. It was actually in pharmaceutical in an air handler unit where one of the cooling coils leaked and water got into the bearings and the friction level went way, way up. And what they did is they greased it to push the water out. Now water was still coming in, so it's not a perfect ending to the story. But we have seen all types of ingress. We've actually seen, this is going to be interesting. It's the amusement park in Orlando. They have bearings underwater to move rides up and down, and they actually grease them underwater, which is I had to see it for myself. I couldn't understand it. So we've seen ones like that as well. We've seen counterfeit bearings. We've seen it. Unfortunately, we've seen a number of SKF counterfeit bearings, brand new, getting put in, and you look at the drive end and the non-drive end, and one's astronomically high than the other, right? And we determined this is a fake bearing. Had none of the properties of it.
So if you have like, let's say a food plant application where they have a power washing bearing every day at the end of the
Yep.
day, you're gonna have reading that bearing changing.
Oh, absolutely.
4 p.m.
Yep.
Day you're gonna have.
Yep.
So that will be calibrated for that particular. The sensor will be noticing, okay, this is just water. Or...
No, so yeah, so no, it still want to push that water out, right? So that's right. So it'll kick in, push the grease out, drop that friction as it's starting up. It'll kick in right away, push that grease out, try to lower it, all automatically. And that's what they're trying to do. We've worked with a number of food plants that try to do it, but there's too many bearings to go out there and try to flush each one. Yeah. Now the correct answer is to stop pressure washing it or build covers around it and stuff. But I understand. Yeah. Can the automatic fluid work in a horizontal direction? What are the environmental temperature limitations? Cold weather. Okay, so can it work in a horizontal direction? Absolutely, it can. It can work upside down if you want to, but again, you guys would know better than me that if you have it in that orientation, oil starts to find its way out and get away from the soap and the thickener and things like that. So yes, it can get mounted in a horizontal direction. And again, with the remote grease lines, you can still mount it any direction and just run a grease line into it. Cold weather, it's darn cold. So we do have some, for Canadian references, up in De Beer mine, things like that. I always jokingly say it's next to Santa Claus. So the reality is the limitation is probably going to be on the grease, not our sensors. And there is a point where just electronics freezes. So we have a MEMS crystal in here and we have a piezoelectric crystal, which is 2 wafers, right? So at some point they're not going to resonate when it's, in Fahrenheit and Celsius cross at like -32, somewhere around there. I'm not sure the exact limitations, but there are ways of mitigating in that cold weather. Around here, the GTA, things like that, there's not an issue. Yeah. Yes. And where's the other mines we have them? So yeah, I think they did put them in some heated enclosures though. I'd have to check for sure, but yeah. 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 A lot of mining in Australia for these. In the middle of nowhere, Australia, apparently. What are the major stumbling blocks in implementation? Maintenance, not wanting to lose hours, bad management awareness of the current situation. I'll say that. So great. We see a lot of people want to put this solution in. The biggest hurdle we've seen is installation. And that's why we went to wireless. And we actually started doing the installation ourselves. So we built up an installation team across the world. We're about 120 people across the globe to do this type of things. And the other part I would say is trying to figure out what you're trying to do. So, and I'm not against unions in general, but you are replacing some tasks that maybe union people have done of lubrication. So working with them, a lot of the times they'll transition from lubricating bearings to using the systems to monitor. They become in charge of that. So you're not replacing them, right? You're just trying to make them more equipped with today's technology. And then the other one from like an upper management level is determining what is the ROI. So what are you going after? Are you trying to save your bearings? Are you trying to save grease? Are you trying to save time? Are you trying to do all three, right? How are you going to justify this program? Please repeat the question from the audience. Okay, I'm going to repeat the question from the audience. Sorry if I didn't do that earlier. How is it sensitive? I'm going to read it on here because I can't read that on the screen. How is it sensitive to probable outer source of noise in addition to the bearing? Okay, great question. So essentially, how do we, first thing I'll answer it in two parts. So the question was essentially, let's just call it environmental noise other than the bearing, right? So one thing I failed to explain is when we're measuring ultrasound, ultrasound is defined as 20 kilohertz and above. Okay, so we are just at the tip of where dogs can hear, but we can't come anywhere near it, right? We're at the 1 to 2 kilohertz. In fact, I have a test here we can do after for fun, and I play the kilohertz until you hold your hand up, and then when you stop hearing it, you have to put your hand down. And unfortunately, people like us that have spent some time in factories or older, we're going to put our hands down pretty quick. If there was some teenagers in here, they keep their hand up. It's remarkable. If you've ever heard the ultrasound things you buy off Amazon or Home Depot, whatever it is, to put underneath your deck to keep rodents away, right? If you bring some young people, they're like, what's that buzzing noise? But we can't hear it. So with ultrasound, we're measuring 20 kilohertz up to 100 kilohertz. So right then there, if you were walk through the loudest factory, just with only sounds that can produce that ultrasound, it's going to get a lot quieter, but it's not quiet. So what we do to mitigate that, and I'll hold it up quickly for you guys on here, but the way this gets mounted is stud mounted. So we put a stud in there and we use a wave guide. The way ultrasound will attach to particularly metal and guide its way up. So when this gets mounted, it gets mounted as close to the bearing as possible, where we have found the highest attenuation of a signal is the grease fitting, because the grease fitting is usually a copper line or a metal line that goes directly into the bearing housing, right? So that allows that sound from the bearing to go direct up through the casing. I'm talking about a motor in this case, right? Through that grease line that sits on top. So properly mounted, we're not picking up any noise. The caveat to that is VFD noise. VFD noise happens to be, if you look at the shunting frequency or the carrier frequency of VFD, usually in the ultrasound range. So what we can do in this sensor is we measure, I can draw it out, but picture a bell curve of how we measure ultrasound, and we can move that bell curve around. So for slow speed bearings, we like to measure it around 20 kilohertz. For regular speed, we're about 30 kilohertz. It gives us the best sound. And what we can do is we can move that around to attenuate the bearing noise and eliminate any noise that's around it. That was a great question. And that's something I could dive a lot deeper into. Can the software and database be on a local server instead of the cloud? on plant network to avoid security issues? Absolutely. And we're developing and testing as we speak. And NERC requirements, nuclear things like that have been asking for it for 2.5 years. So that's why we've developed it. So even I didn't get into any of the insights, the AI that's using to detect anomalies. So we're doing just a basic anomaly detection on all the variables that are coming in. Can all be done on premises on a local machine, as well as customer cloud or our cloud. Great question. Okay, I do think this presentation will be made available, and what I'll make sure is, and the one thing we did miss is those sound files. It's always interesting to hear it, so I'll make sure those get included with it. For anyone that wants to hear it, I would recommend displaying those sound files because then you'd be able to really hear that. And I'm sure there's a way of getting in touch with me. We can put my name out there and email. So if there's any questions, feel free to reach out.
That was fantastic. We have a last question. Is any mobile equipment, off-road equipment, drills, anything that you tested this before?
We've been on anything that's moving.
Excavators, anything, autonomous trucks, CAT 793, 797s.
I'd have to say our mining guy. I'm sure he's probably strapped into it, but nothing I can think of.
Okay. All right. Thank you very much. Thank you. So just quickly go through some closing remarks. I think that we got several people still connected. Thank you, Bechat, for doing all the IT work. Trying to see here. So we just want to mention very quickly there for the people in the room and the people that are connected that the next presentation is going to be November 14. We are looking at doing a tour of the lab wear check in Burlington. And Bill Kennell will be presenting and also providing the tool for us. Thinking about to do that probably between 2 or 3 p.m. So we have time for do the lab tour at the Burlington location, and then the presentation by Bill Kennell, and maybe some kind of networking and so on. So that's pretty much for the day today, and thank you for connecting. Thank you, Richard.
Thank you, everybody. Thanks.